So first of all, of course, I would like to thank the organizers for the invitation to give this talk. So the title is on the blackboard, and as you can read, this is joint work with Markus Pflaum and Shang Tang. Okay, so my plan for today is actually first to give a motivation for what we are doing. Then I want to present to you two theorems, sort of carefully write them down. Then I want to say a little bit about the proof of those two theorems, and if time permits, well, look a bit further for applications, etc. So for the motivation, I want to go back to the most well-known index theorem that's around, and that's the Atiyah-Singer index theorem. So we have already seen it on Tuesday, I believe, but I'll briefly recall it. So if we have a compact manifold, and I have an elliptic differential operator, then first of all, this operator is Fredholm. So I can talk about the index, and the Atiyah-Singer index theorem gives an expression for this index as an integral of some characteristic classes that are related to the manifold M and the operator D. So this is a characteristic class that's intrinsically associated to the manifold M, and so sigma of D. So sigma is the symbol, and you can take the sigma. The symbol determines a K-theory class. You can take the Chern character of that, and in the end, you end up with a differential form which is closed, and you can integrate it over T star of M, and then the theorem says that that is equal to the index. So there is a generalization of this index theorem that's due to Kohn and Moscovici. Where they generalized just this one index of this operator to a pairing with even cohomology classes on the manifold. And this is sometimes called a higher index pairing. So let me write L of M as the set of elliptic differential operators, and it's a pairing with even cohomology classes of M. So it doesn't take values into the integers. That's something that you give up. So it takes values in the complex numbers. And the generalization, so I'll briefly say something about the definition in a few seconds. But the definition is such that, so let me write that, it's bracket, that if you pair an operator with the trivial class 1, then this is equal to the index of D. Okay, so basically these are two theories, and as you can see they are related in some sense, and this I want to generalize this picture to Lie groupoids. So in the next few minutes I'll try to convince you in fact that something like that is possible, that you can already see some groupoid playing a role in this whole theory, and also some Poisson structure. So let me make a few remarks. So first of all, just one way to rewrite the ordinary index, and I mean not write it as the dimension of the kernel minus the dimension of the co-kernel, is to notice, so by definition, if D is elliptic, this is equivalent to well, the existence of a parametrix which is, or you can construct it as a pseudo-differential operators that inverts the modulo the smoothing operators. So such that dE minus 1 is in psi minus infinity of m and ed minus 1 also. So the smoothing operators, so they have a smooth kernel. So I can also think about this as just the C infinity functions of m times n. I've assumed that m is compact. I think it should be up there. Yes, m is compact. Okay. And another way of thinking about this is also that I can think of these as sitting inside the B1, so that's trace class operators on some L2 space of M. So I can take the trace of such guys, and well, once you've constructed an E that has these properties, so from E you can construct what is called an index class, and this lives in the K-theory of psi minus infinity of m. So is represented by an idempotent let's call it E of D, that lives inside some matrix algebra over psi minus infinity of m. So ED squares to itself. And so this, by the way, this construction is a sort of a completely standard K-theoretic construction. So this
represented by idempotent or a formal difference by idempotent?
Actually, it's a formal difference, yes. I'm being a bit sloppy. Okay. The essential point I want to make is, well, I have a matrix algebra over this psi minus infinity of m, but I can still take a trace. So I first take a matrix trace, and then I take the trace that I have over here, which is just integrating over the diagonal. And in the end, you write the index of D as the trace of this idempotent, or actually formal difference of idempotent. So this would be something like integrating over M the matrix trace of ED x, comma x. Okay, so how is the higher index defined? I just want to give you sort of a glimpse of, well, what could be worked out to be a real definition. So I have to pair with an even cohomology class, and the idea that Conor Moskowitz had was to represent a cohomology class by an Alexander Spanier co-cycle. So represent alpha, well, let's say of degree 2k, of M. An Alexander-Spanier co-cycle. So again, I want to be not too precise. So this is alpha, and it's just going to be some function on some Cartesian products with M by itself. So when I say co-cycle, I mean that there is a differential, and it's supposed to be close to the differential, but I won't explain it to you in the end. So the key point is going to be, that this M cross M, we can think of it as the pair groupoid. So we know when we have a Lie groupoid that there is something called groupoid cohomology. There's a groupoid cochain complex, and if you sort of work it out for in this case for the pair groupoid, you will find out what the differential is. There's a subtlety with regard to localization, but that's something that I want to address later. Okay, but anyway, if I have such a function, at least I can write down a formula of the following kinds. Where I integrate a bunch of these idempotents after multiplying it with my Alexander-Spanier co-cycle, and I integrate over dx naught to dx 2k. So, as I said, I mean, it has to be worked out, so I have to also take a trace over the matrix. So these are matrices, so these I have to trace out. So then I can in the end integrate. Okay, and the final remark I wanted to make is that both theorems, so one way to derive them, and that's not how they were originally derived, but I think for this audience it's fitting. So both theorems can be derived from what is called the algebraic index theorem. For the canonical symplectic structure on the cotangent bundle of M. So when I say algebraic index theorem, so I mean the one of Nest-Siegen. And the Atiyah-Singer index theorem, there was also an index theorem, or the same index theorem by Fedosov, and with Fedosov version you can derive the Atiyah-Singer index theorem. In principle, this is a little bit more general, and you can derive the general pairing. Yes?
I have a question about the higher index pairing. The modulo of origin H even is K0, and then you have an index pairing of elliptic operator with K0. Are these two pairings related? Or?
So you're asking about K-theory?
Yeah.
Yes. So I'm deliberately not mentioning this because it's a little bit more difficult than that. So can I answer this question? Let's think. No, let me answer it later. I think it's better. Yes?
Which is the second theorem? I mean, the pairing which is here is the definition? Or
Yeah, so this you should read as sort of my attempt to give you the definition. And then here... Oh, dear. So... I completely forgot to state the theorem, yeah. Okay, so I'll write it down here then. So the theorem, so thank you for that. And that is what is called the higher index theorem. It says that the pairing between D and the cohomology class alpha is 1 over 2 pi square root minus 1 to the power k. integral. Well, you see the usual classes appearing. But now you integrate using a different degree of this class, because you wedge with the pullback of your cohomology class alpha, where pi is the projection to M. Okay. Yeah, so I'm sorry for this order, but this is more or less a definition, and this is the theorem. Okay, so I think now it's pretty clear. So the goal is actually to replace the pair groupoid by any Lie groupoid and derive similar theorems. Okay. So I have to set this up in a proper way. So let me tell you the notation that I use. So G is going to be a Lie groupoid over a base space M, and I denote its associated Lie algebroid defined as the kernel, the derivative of the target map restricted to M. I denote it by A. I have an anchor row, or let me maybe write row sub A. So that's a map from A to the tangent bundle. So I'll need a few things. So first of all, I need the following fact, which was first pointed out by Evans, Liu, and Weinstein. So if I form the following real line bundle by taking the top exterior power of the cotangent bundle of my manifold M, and I tensor it up with the top exterior power of the Lie algebroid A, then that carries a canonical action by the Lie groupoid G. So is acted upon by G. So this is remarkable because, so as we all know, there's no canonical adjoint action. There's no representation up to the nose of the Lie groupoid on the tangent bundle or on the Lie algebroid itself. But apparently, if you take this combination of top exterior powers, then things cancel, and G really acts on this Lie algebroid, on this line bundle. So I can speak about the following cohomology. I can form the differentiable groupoid cohomology with values in this line bundle. So at this point I'm very grateful for the school that was here last week, because I don't have to explain how to define this, as if I'm correct. Okay, so that's one thing I need. I need this line bundle. I need the groupoid cohomology with values in that line bundle. So another thing I need is the convolution algebra of the groupoid G. So this is formed in the following way. So I'm going to denote it as A subscript G. So these are compactly supported sections on G of the pullback, the top exterior power of the dual of A star. So actually it's better to use densities, but I'll ignore that. At least for this talk. And I need to define a product on this space. And this is done as follows. So if I have two sections over G, then, well, I need to produce a new one, and I'm going to evaluate it at G, and it's given by an integration of a G sub target of G F1 GH inverse F2 H. I have to integrate out H. So here's a remark. So first of all, G sub x is all arrows in G having target equal to x. So that explains the notation that's over here. And second of all, if I look at F2 in H, so that's an element of the top exterior power of S of H, of A dual S of H, and this is isomorphic to the top exterior power again of the kernel of dH of T, and this is the top exterior power of T star H G sub T of H. So this is to convince you that actually, well, if you do this careful, and more careful than I'm doing it now on the blackboard, then in fact you will see that it does make sense to integrate. So I'm writing dH just to indicate what you should integrate, but this is in itself already a form that you can integrate over the fiber of T. Yes?
Is this equivalent to the space that Kahn defines using half densities along the...
I think it is, yes. I think it's a matter of choice. So somehow I developed a preference for sort of putting the densities really not sort of half on source and target, but you really make one choice. But I think it's the same. Okay, so from the point of view of non-commutative geometry, this is actually sort of the starting point of why you should look at Lie groupoids, because they give sort of models for interesting non-commutative algebras. And so one of the big themes is actually to understand this convolution algebra, and most notably to understand the K-theory or cyclic homology of this algebra. So that's sort of another motivation for this thing that I'm doing today, but then from the point of view of non-commutative geometry. Okay, so then I'm almost there with my setup. The only thing I need is the universal enveloping algebra. So I'll denote the universal enveloping algebra as U of A, and so there are two ways to define it, and I'll just say it in words. So one is sort of a rather algebraic way, just using the Lie algebroid, but since I'm always assuming, and maybe it's good to stress this already from the beginning, I always sort of have a Lie groupoid that has this Lie algebroid as its Lie algebroid. I can also think about this as invariant differential operators on G. I'll explain that later on in a more precise way. So it's a non-commutative algebra that's canonically associated to A, and there's a Poincaré-Birkhoff-Witt theorem that tells you that U of A, it's a filtered algebra. Well, if I tell you that it's invariant differential operators, they have a degree, so I can filter it, and the graded space is isomorphic to the symmetric algebra of the Lie algebroid A, and this is induced by a map sigma. That's the symbol map. So I need to slightly sort of get a slightly bigger algebra for what I want to do. So if I have any vector bundle over M, then I want to consider the tensor product of U of A with the endomorphism bundle of E. So this is obviously a tensor product that you can form. And then I need the notion of ellipticity. I mean, it says bundle, so over C infinity of M if you wish. So I'm going to say that an element in here is elliptic if and only if I take the symbol and evaluate in a cotangent vector, then this should be invertible. When I say cotangent vector, I mean vector in A star. Okay. So this is all the preparation that I need to state the theorems that I would like to explain. So the first theorem is going to describe two pairings, and it's going to give the relation between the two. So first of all, so there exists canonically a pairing between the K-theory of the convolution algebra of the groupoid that I'm considering with the even differentiable groupoid cohomology of G with values in A, and it takes values in the complex numbers. So this is on the level of K-theory. Second, there is also a pairing between elliptic elements in A, well, or even, if you want, I can put in this vector bundle E, so it can act on vector bundles, and it's going to pair with Lie algebroid cohomology. Again, with values in this representation L of A, again taking values in the complex numbers. So third, so for D, an elliptic element in A with values in E, first of all there exists an index class again we write it as index of D in the K-theory of A sub G, such that for all groupoid cohomology classes I have to go to a new blackboard. Such as blah blah blah. So if I pair this index class with the groupoid cocycle, that's the same as pairing the operator D with the second pairing with the Lie algebroid cocycle, that I write E of phi, where E is a canonical map from groupoid cohomology to the algebroid cohomology. That's known as the Van Est map. Okay, so that's the end of the theorem. So, just to say it again, so there are two pairings, and actually, if you're interested in the K-theory of this convolution algebra, or the cyclic homology, then actually the first one is what you want. You want to evaluate this pairing to find out if certain K-theory classes are non-zero or not. So you should read the theorem as follows, namely that you can actually, by the third property, evaluate it by pairing with the second pairing with the induced Lie algebroid class that you get from your Lie groupoid class. Okay, so the second theorem that I want to state is going to tell you that this method is successful because it's going to give the answer of the second pairing. And so by that you then have sort of solved completely the evaluation of the first pairing. So theorem B. So let A over M be an integral Lie algebroid. I'll comment on this integrability in a second. D is again going to be an elliptic element with values in E, and alpha is an even degree 2 K Lie algebroid cocycle with values in L of A. So then the pairing between D and alpha is given as follows. So it's 1 over 2 pi square root minus 1 to the power k integral over the dual of the Lie algebroid. So that's the Poisson space we're interested in. And I have again terms that look quite familiar, but perhaps not quite. Churn of sigma of t. And again I have to pair with my groupoid cocycle. So maybe I should lift this blackboard. So So I want to comment on this formula. So in principle, I just want to tell you that this is a very concrete formula. You can evaluate it. So this is a characteristic class that you can simply compute. Well, you can take the Chern character again of the symbol of your elliptic operator. So that's going to give you the Remark homology class on A star. Okay, but then apparently, so I pull back along the anchor of some Lie algebroid that lives over A star, and I integrate also with respect to the Lie algebroid class that I have over there, that I started with, that I pair with. So I have to tell you what this pi shriek of A is. Okay, so maybe first one comment. So I'm writing here integral Lie algebroid because the way we prove this theorem is actually to use the groupoid that integrates the Lie algebroid that sort of was around already from the sort of setup of the theorem. But then, so you derive the theorem, and well, at some point you have the impression you're writing down a purely Lie algebroid statement. But so our proof uses the groupoid, so I can't really sort of just write let A be any Lie algebroid. I have to write that it's integrable. I have to say something about this pullback Lie algebroid. So this is a construction that's due to Mackenzie and Higgins. So if I have a Lie algebroid over a base space M, and I have a submersion from P to M, then so one would like to have some kind of pullback construction in the category of Lie algebroids. So the sort of ordinary pullback of A as a vector bundle is not going to help you. So the thing you do is the following. So you define pi shriek of A, and it's defined as follows. So it's so I'm going to describe to you the vector space at a point P. So this is given by pairs of xi, x that live in A. Okay, so apparently I used the wrong notation. I have to write pi of pi sub P plus T P P. And there's a condition, and that's actually where it sort of starts to differ from the ordinary pullback, namely that the anchor of xi equals the derivative with respect to pi evaluated at x. So this is the description of the vector bundle, and then, well, there's an obvious Lie bracket. And there's an obvious anchor mapping, and I leave it to you to check that this is indeed a Lie algebroid. Okay, so in our case we are applying this construction to the projection map of A star to the base M. So I have pi shriek of A, and I now have two projections, one to A star over M. Oh, this is something I probably should do it the other way, to just fit it into my picture here. Like this. So it comes with a special structure, namely it has a canonical symplectic structure, because I have here A and A star. So let's give a name to these projections. Pi of A, PA star. So there's a canonical symplectic structure. Canonical symplectic structure. Theta, and it's just given by the projection and the evaluation between A and its dual. So I have now a Lie algebroid. I have in fact a symplectic Lie algebroid over A star. And so one thing, since I'm working with Lie algebroid cohomology, I want to make sure that by sort of using this construction, I don't sort of lose all the information in Lie algebroid cohomology. But from a result of Marius Kreinig, in fact, we can deduce that it doesn't. So the Lie algebroid cohomology of A with values in L of A is canonically isomorphic to the Lie algebroid cohomology of pi shriek of A with values in the pullback line bundle. So actually the statement is, well, I don't want to write it down, but it says that if you pull back the line bundle, then canonically it's a representation of pi shriek of A, and so you can consider this Lie algebroid cohomology, and it's isomorphic to this one, and there's a canonical map going this way, and it's just pulled back along pi. Okay, so of course I don't want to touch this. So there's one more thing I need to explain to you, and then at least you can understand the statement. So then I have succeeded in what I wanted to tell you. So I have this canonical symplectic structure. So using theta, I can take the top exterior power, and that you can use to get an isomorphism between the pullback of L of A and the line bundle associated to this new Lie algebroid pi shriek of A. So this is basically tensoring with the top exterior power of theta. And with that, I can now define a pairing between the kth Lie algebroid cohomology of pi shriek of A with values in pi shriek of A. So compact support over here, values in the complex numbers, that's given by, if you take two differential forms for pi shriek of A, then you will integrate them over A star alpha wedge with B. And if you think about this, then this guy over here is an element of the top exterior power of T star of A tensor top exterior power of pi shriek of A tensor top exterior power of pi shriek A star. So you can contract these two, and then you get a volume form and you can integrate. Okay. So that's for this statement. So now I've explained to you how to, in principle, integrate all these terms. So now it's well defined. So I have to think, how much time do I have actually?
13 minutes.
13 minutes. Okay. So I want to say a little bit then about the construction of this pairing. Because there's still some things unexplained in there. Okay, so first of all, let's say 3.1. So to define this index class of K naught of A sub G, so we use the pseudo-differential calculus for Lie groupoids by Nistor, Weinstein and Zhu, and also I think by Montrubert. So that gives you a filtered algebra psi infinity of G of actually families of invariant pseudo-differential operators, and there are two properties that we need. So two properties. So I'm not going to define it. So first of all, if you look at the smoothing operators in this theory, and you're careful about the about the support, then this will in fact give you the convolution algebra of your Lie groupoid back. Second of all, we have that the universal enveloping algebra of A sort of injects into psi infinity of G as invariant differential operators along the T fibers. Along T fibers. Okay, so as I said before, when I explained the Atiyah-Singer index construction, I said there was sort of an automatic K-theoretic type of argument, and in fact this suffices already for the elliptic of A to give me an index class of D in the K-theory of the convolution algebra. So that's done. That's more or less automatic. And that's needed in the third statement. Okay, so I need to tell you how to pair. Well, I can't really sort of give the precise details. So the global pairing. So assume for a moment that the groupoid is unimodular. So that means that I can find an invariant volume form, well, volume in gamma infinity of L of A. And this is going to give me a trace on the convolution algebra. Trace tau omega f given by integrating over m f contracted with omega. Just to remind you, so L of A is top exterior powers of A tensored with top exterior powers of T star of M, and F itself was a section of the top exterior powers of A star. So I can contract the A with the A star and integrate over M using the density that I get. So this defines a trace on A sub G. So this already gives me one index, which is basically the sort of the Atiyah-Singer type of index that I, if I have a trace. Okay, so to get the other classes, or to get sort of higher degrees, so I'm not going to tell you how to do this, but well, you will need some cyclic homology. So cyclic homology is sort of a generalization of the notion of a trace on an algebra, and it's actually sort of developed to pair with K-theory. And in fact, so if you do it really carefully, you will find that there is a canonical map between the groupoid cohomology with values in this line bundle and the cyclic cohomology of this convolution algebra A sub G. Okay, still don't want to touch this one. Okay, so this is all sort of sketches of what's involved in the proof. So, and the last bit is actually to use the localization to the unit space. So here I really have to be very sketchy. But, so if I have this pseudo differential operators on the Lie groupoids, so there is a quantization map from sort of a symbol space on A star. And as you sort of, well, these are sort of certain functions defining certain growth conditions. And as you sort of compose pseudo-differential operators, you will find that so this induces a star product on the dual of the Lie algebroid A star, quantizing the Lie-Poisson structure. Now in this quantization map you have a lot of control on the support of these pseudo-differential operators, and in fact you have the ability, once you've sort of constructed this trace class, to represent, once you've constructed this index class, to represent it by idempotents that have support around the unit space that sort of gets closer and closer to the unit space. So in the end you can sort of localize the pairing to M inside G. So I have to tell you how the Lie algebroid cohomology then shows up. And that is in the following way. So So if I take the standard differentiable groupoid co-cycles, but I require the supports to be inside some neighborhood U of the so U is some neighborhood of the unit space, and the support of the co-cycle should be in there, then as I sort of take the direct limit over these U's, I will get a complex, let's write it as C hat, that's perfectly well defined. So I also get a differential, delta hat, and it actually computes something new, or something different, not groupoid cohomology, but it's the Lie algebroid cohomology. Wow. And there's of course a canonical map that sends any groupoid co-cycle to its germ or its infinite jet around the unit space, and that is really just this Van Est map that appears in here. So I'm using a slightly different complex to compute the Lie algebroid cohomology. So and as a result, I mean, usually in the Van Est map you see the sort of the exponential map appearing, but because I use this other complex, the Van Est map is extremely simple. It's just restriction, well, it's sort of taking the germ around the unit space, but in fact, so the exponential map is hidden, of course, in this isomorphism. Okay, so I think this is a good time to start. Or maybe one more thing. You can actually now go back to the pair groupoid. So that's maybe one comment. So the pair groupoid. So the pair groupoid is proper. So there's only one interesting, or one non-zero differentiable cohomology class, and that sits in degree 0. So it means that in this theorem with this pairing, okay, so you first have to think a bit, but L of A is actually canonically trivial. So this pairing, you can only pair with one class, and if you think about it and you write down what you find in the end here, you will see that this is just the Atiyah-Singer index theorem. But so the Lie algebroid is of course T of M. over M, and the Lie algebroid cohomology is simply the Remark cohomology of M. And once again, if you go back to the second statement, you will find the Kolmos-Kovic localized index theorem in this case. So it's really a generalization. So I think that's a good moment to stop.